we already see many different games, right? So next one, also something interesting. So now we are heading outdoors, right? At least in spirits, right? So for a journey through the Singapore Zoo, but it is not just a walk in the park, right? This team from Temasek Junior College takes on the challenge of finding the best route through dozens of attractions using the mathematics, with graphs, algorithms, and a dash of curiosity. They've mapped out the most enjoyable paths on the real-life streets. So let's now follow their trail and pay a visit to the Singapore Zoo. Okay, please.
By the nature of our graph being a weighted graph with non-negative edge weights, we decided to use a modified variant of Dijkstra's algorithm. Firstly, let's go through what the classic Dijkstra's is. Dijkstra's is a single source shortest path algorithm that finds the shortest path to all other nodes that's starting from one node. Dijkstra's works by processing paths and increasing total time spent. Therefore, when reaching a node for the first time, the minimum cost needed to reach that node is guaranteed to be that walk. So other paths going through the same node later on need not be processed. In our project, our objective is to find a one cycle with the maximum possible enjoyment value such that the total time spent is less than or equal to x, where x is a variable parameter. Our modified variant creates copies of each node for all distinct attraction edges visited. Therefore, if the number of attraction edges is n, the number of copies for each node is 2 raised to the n power. This is due to the fact that each attraction edge could either be visited or unvisited in a walk. Let's define a state to be an ordered pair that comprises the node and the current set of distinct attraction edges visited. Hence, if we reach a node again, as long as the set of distinct attraction edges visited is different, we do not terminate the search. This is because it can be sometimes more efficient to visit new attractions by revisiting nodes. To further optimize the time of our program, we decided to utilize search pruning to skip any walks that are guaranteed to be non-optimal. For our case, we terminate the search as soon as we reach no one again, and we store the current walk as one of the one cycles to be considered. So, why are one cycles that reach no one as an intermediate step guaranteed to be non-optimal? To set the context, the time of the edges 1, 2, and 1, 3 both have a greater time value than 2, 3, and also none of these edges have a non-zero enjoyment value. Additionally, node 1 is also not an attraction. Suppose the one cycle taken is an arbitrary sequence of nodes as shown on the slides, where xn and xm are either nodes 2 or 3. Let's consider a first case where xn equals to 2 and xm equals to 3, or vice versa. Since the above mentioned edges have no enjoyment and node 1 has no attraction edges incident on it, there is no possible way for a change in total enjoyment when traversing the walks across the nodes 213 and 312. Hence, they result in the same outcome as 2-3 and 3-2 respectively. Since the latter option has a lower time spent, it is not possible for an optimal solution to first pass through node 1 in this case. Now, let's consider a second case where xn and xm both equal to node 3 or 2. In this case, traversing either the edges 1, 2 or 1, 3 twice would not result in a change in total enjoyment. Thus, this would result in a greater time value without actually contributing any enjoyment and cannot be optimal as well. Now, I'll pass the time to Matthew to discuss how we implemented our algorithm. It does not revisit nodes for the possibility of better solutions. By allowing the revisiting of nodes, our revised approach enables a more optimized and flexible routing by considering the shortest path to a node in a specific state. Finally, although our final solution is rather of an estimate, real-world applications tend to favor effectiveness over perfection. So, how could we deploy our algorithm in real life? Well, firstly, we can deploy our algorithm in various travel suggestion apps for tourists, such as in the Mandai Zoo app itself, so that tourists will be able to explore the zoo to their fullest potential when on a time budget. In a similar way, we can also incorporate our algorithm into AI assistance portals. Therefore, with our revised approach, we can now help Curious George visit his friends in an optimal way. Thank you for listening to our presentation.